what is a reasonable estimate for the density of sand? So we have two values that are grams per centimeter cube and two values which are kilograms per meter cube. Now for consistency, I'll convert the bottom two to grams per centimeter cube. And I could do it the other way as well, but I just prefer to do it this way. So this is going to be 0.02 grams per centimeter cube. This is going to be 2 grams per centimeter cube, right? And just to keep it in check, the first one is 2000 or 200 grams per centimeter cube. And this is 2000, right? So huge numbers, right? Like very different. So it's kind of easy to do. For one thing, we know a glass of water will have or water of anything of water will have a density of 1 gram per centimeter cube. Facts, right? Now, another thing we know is that when you put sand in over here, it's gonna sink to the bottom, right? That tells us it's going to be higher than 1 gram per centimeter cube, so we can rule one out. That's the obvious one, right? Now, how do we do this from here? So all other values seem to be higher. How do we do this? Now, think about this. If I had, if this was on a balance and there was no sand inside, if this was on a balance, how do I make a balance out of this? This on a balance, right? This is my attempt at making a balance. How much sand will I need to put over here to have this balanced out, right? So somewhere about this amount looks fine. Maybe it's slightly less, right? So that tells me the glass of water will be very close to, so it's not like 10 times heavier, right? It's not 1,000 times heavier. So it's in the same order, right? So sand can be 2,000 times heavier, or it can be 200 times heavier, because that would imply that only a tiny amount of sand, let's draw, instead of this, only a very tiny amount of sand should be able to outweigh this glass from over here. So that tells me that, so these are huge values compared to our 1 gram per centimeter cube. So I'm going to go with the only viable option at this point. I'm left with this, 2 grams per centimeter cube. That's my answer. A ball strikes horizontal surface at a momentum p at an angle of theta to the surface as shown. The ball rebounds. So it comes over here, hits it, rebounds. So there's a change in momentum. So it's in contact with the surface for time t. So during that time, it's undergoing a change of momentum. What is the magnitude of the average resultant force? So the average resultant force, or just the force experienced by the ball, is F. And the relationship with force and momentum is the change of momentum, right? Change in momentum per time. That's the relationship. Now, not all the components of this momentum vector are changing. And you can tell which one is changing. Only the vertical component is changing, because it's here, then it's going out there like that, but the horizontal remains the same. So if I were to resolve this, that's the horizontal component of our vector, and that's the vertical. This angle is theta. So the vertical component is going to be P causes with the angle sine theta. Sine theta, right? Now from this momentum, that's the vertical component, it's changing into P sine theta again, right? So, but this is in that direction, right? Upwards. So it had this momentum downwards, now it's upwards, so the change would be double of this value. So the change in momentum is 2p sine theta over t. And our answer is 2p sine theta over t. A skydiver who is falling vertically through the air opens his parachute. So he's been falling for some time, so you know he's has high velocity, which describes the velocity of the skydiver immediately after he opens his parachute. So as soon as he opens it, he's going to start undergoing deceleration, right? So let's bring our skydiver over here. I wonder why they didn't move together. Okay. Okay. Right? And so right now he's undergoing, right before he opens it, he experiences acceleration downwards, right? Which is g, at a value of g. But as soon as he opens it up, he's going to experience a greater drag force because his velocity is going to be high. So drag force, and slowly, as the velocity of his velocity decreases, the drag force will decrease until it'll match the gravitational force, and he'll undergo no net acceleration, and he'll attain his new terminal velocity with the parachute enabled, right? So what's happening to his velocity? So his velocity is going to be really high while he's falling downwards. So that's his initial velocity. Let's call that u. And right after his velocity, I'll just put it right next to it. Doesn't make sense too much. As soon as he opens the parachute, his velocity he'll still be moving downwards, right? But it'll be less because of the parachute, and it's gonna decrease like this. It's gonna decrease all the way until, so I'm imagining a graph over here. So it's gonna as time like this, and his velocity will constantly decrease until it reaches 0. If this makes sense, I'm just being very visual right now, right? So the vector direction of velocity is downwards, and the velocity is decreasing. Our options tell us that the correct answer is A. A particle with mass moves in a horizontal straight line through a uniform electric field in a vacuum. The electric field is vertical. Okay. There is significant gravitational effect on the motion of the particle. So it's being, weighed down, so it's being pulled down because of gravity. What could be the direction of the electric field? It's a pretty straightforward question. So the particle is experiencing gravity, so its path should be like that, but we see that it's actually going straight, so there should be a counter force acting on it as well. That's probably trying to pull it upward as well. So let's draw that upward as well, and that's probably because of the electrical field. Now, electrical field, we want to figure out what is the direction of this electrical field and what is the sign on the particle, the charge of the particle, right? So what could pull it up is, now I know electric fields if an electric field is pointing like this, right? If a field is pointing like this, I know for a fact that if it's pointing like this, this is the path a positive charge will take in the electric field. That's the definition of an electric field line, right? So if the charge had a positive charge, right, and if it wasn't moving horizontally, it would move downwards, matching this line. So this charge, if the electric field is downwards, has to be negative for it to move upward. It would now move upward. And that's what we want, right? We want the force to be upwards. So either this could be it, or the opposite of this, where the charge is positive, but the electric field lines are pointing up. Let's see if we can find that in our options. It's downwards, the field is downwards, and the charge is negative. That, okay, we already found our answer. But let's see any other combination is correct. Look over here, upwards, but it has to be positive, but it's saying no charge. What's that going to do? absolutely nothing. So they negated that, and our correct answer is just A. Very routine question. This ball right over here is in equilibrium, is in dynamic equilibrium. It is not moving, right? And so whatever forces are acting on it, they're keeping it, holding it in position. So they're all balancing it out. So let's identify how many forces it has. One is the obvious one, which is already written down, a force F, right? And that's straightforward. So no issue there. The other force acting on it is the weight of the ball, which is going to be close to 300 newtons. So that's acting on it, 300 newtons. So force 1, force 2, and it doesn't look like in equilibrium, but there's a third force right now, which the string is causing it on the ball, which is the tension in the string. So let's call that T, right? So now it's in equilibrium, and we have to figure out how much force is being used on the ball right now. So that looks like a very challenging question, but if you recall anything from your days in maths and simultaneous equations, if you can make two equations with two unknowns, you can quickly solve it. So, and just by resolving the tension vector, we can easily do that. So the vertical component of the tension vector will be this. And what's the angle going to be? What is the angle going to be? This angle right here inside is 30 degrees. It's going to match this angle, right? So let's erase the marker. All right, that's 30. I'm not writing it down because I don't have space. So the vertical component is T cos 30, right? T cos 30, which is being balanced out by 300 newtons. So what's T now? What is T? Let's figure that out. Putting it in my calculator, 3 comes out to be 346 newtons. I'm approximating it. It's point something, but I don't care because it's an MCQ, right? So that makes sense that T is larger than the component of T. So I did something right? The horizontal component of T is going to be obviously be T sine 30, which is going to be equal to the force F, right? That is because the horizontal component is going to be, I can draw it over here like this. Let's just put it over here. That's the horizontal component. And that's being balanced out by the force F because it's in equilibrium, right? So 346, that's easy. And that's just half of 346. 346 sine 30 is equal to F. So F should equal to now, divide this value by 2, 173. And I think the best answer over here, let's put newtons here. Best answer we have is 170. That's our answer. An aircraft travels at a constant velocity of 90 meters per second in a horizontal flight. The diagram shows the horizontal force acting on the aircraft. So it's at constant velocity, so it's in equilibrium. And the drag force is 2400. That means the power being mustered by the engine, the thrust, is actually, why do I have this? Is actually the same. So the engine is producing a force of 2400 newtons. Okay. And the velocity, of course, is V. What is the power produced by the thrust force? Okay, not talking about the engine. The mass, the power produced by the... So I think this is trying to confuse us. We don't really need this information, I feel. And the power can easily be generated or calculated, by the equation force times velocity. Because the force is being generated depending on how heavy this is. If this was heavier, the force would be obviously be more, right? So I think that makes sense to me. So that's kind of, what I'm trying to say is the mass is kind of accounted for already, so you don't have to put it in the equation again. So the force is 2400 and the velocity is 90, and the power I should be getting is 2400 times 90, 21.6 kilowatts. Do we have that? We have 22. That's 2.2 times 10 to the power 4. I'm getting 4. They're saying 5 over here. I made a mistake. I'm actually getting 216. So this dot is not really here. So that makes sense now. So over here, I should be getting 2.2 to the power 5, right? An exact value. That's cool. B is our answer. The correct answer is B. A wire is stretched by applying increasing values of force F. For each value of force applied, the extension X is recorded. A force extension graph is plotted. Which statement about the area under the graph must be correct? This is true if the wire was extended elastically, right? So if it was under behaving like a completely, truly elastic object. So we're not sure, and only if it was would this be true. So we can't be confident about this remark because we don't know if the wire was a true elastic piece of material. It is the elastic potential energy stored, again similar, same point as this one, just rephrased. It is the work done. So the work done, the energy inputted into the device. I don't know if it all got stored in the device, not sure, but that is the work done on the object. So the energy being applied to the object, or the amount of exertion I went through, and it was completely elastic. The work done on it would convert completely to its potential energy. That makes sense. It would be the same for any wire of the same material, but different length would give you a different result, right? So this is off as well. So C is my best bet. A source of sound of frequency F at point Z is moving at a steady speed. The pattern of the emitting wave fronts is shown. So Z is moving from right to left towards that because it's much smaller over here, which further describes the frequency of the sound heard by a stationary observer, a Doppler effect, right? X and Y. So the frequency being emitted, so per time as these circles are getting larger, and they'll get larger at a uniform rate, X will experience a lot more because they're just closer together. Or in more technical terms, the wavelength is much smaller. So the frequency for X is going to be, so for X, the frequency should be greater than F. And for Y, the opposite, where it should be less than F. So if the car or whatever object is emitting a frequency, they're hearing, right? So, and that makes sense. So, like a car moving. I'm trying to recreate the Doppler effect, and that makes sense, right? Okay, so what's matching this? Less, greater, less for some reason. So C, easy question. The two waves P and Q meet at point X and superimpose, so they're interfering constructively. That's the word. Initially, the two waves meet at X in phase 0, so they're gonna add, the amplitude is gonna add up on top of each other. So the resultant wave has an amplitude. So it's P and Q. So wave amplitude of P will add to amplitude of Q, and the resultant is 14 centimeter. It's 14. That's our first equation. It looks like a simultaneous equation. Phase difference between is 180, and the resultant amplitude is 4. So the difference is 180 P minus Q. It could be Q minus P as well, right? Not too sure there, but it shouldn't matter. What is the amplitude of one of the wave? Yeah, so it doesn't matter. So whatever is subtracting, it doesn't matter because the smaller one's subtracting, and they want to know one of the wavelengths. So P minus Q is equal to 4. Rearranged, P equals to 4 plus Q. Put that in equation 1. That's P. Oh, P is already there. Oh, P I have to change, right? So P is 4 plus Q. And continuing from the equation, plus Q is equal to 14. That's 4 plus 2Q equals to 14. That's 1 plus Q equals to 7. Q equals to 6. Right? I don't see 6 here. So they're probably talking about the other value. Right? So Q, 6, put that in here. And easy peasy, I'm getting PS 10. And that's our answer. So they were asking for one of the waves. So the first one we ended up calculating, coincidentally, was not the one they were talking about. So there, did I say wavelength or something? I'm sorry, misspoke. The amplitude. I was talking about the amplitude. So there are two waves of two different amplitudes, P and Q. And at one point, when they join together constructively, the resultant amplitude is 14. And when they do it destructively, it's 4. And with that, they're asking, can you tell us the length of the amplitude of one of the waves? And we found out this one first very easily, and that wasn't in the answers. So they were probably talking about the other wave, the one with the higher amplitude, and we used Q's value to find P out, and 10, pretty straightforward. Two sources of microwaves P and Q produce coherent waves with a phase difference of 180. So it's not a double slit experiment. These are two different waves. How do I know? Because they're saying they're 180 degrees apart. So it's not the same light source being emitted from one light bulb or one microwave oven over here, right? So they're already 180 degrees apart. So they're trying to trick you, right? Right? So the wavelength has the same, so they're essentially the same light, but they're starting different. So they're just, so one is leading, one is lagging, right? So they're apart by 180 degrees. So if they would meet in the center as a diffraction thing, they would form a minimum, because one is, let's say this one is already 180 degrees out of phase, and this is not out of phase. This is like, legit. Right? So this would have a minimum over here. So it's a reverse pattern we'll see. So minimum in the center, minimum light intensity in the center, or microwave intensity, and the reverse, right? At point S, there is a minimum. So over here, there's another minimum, right? For that to happen, so it's confusing because they've changed the settings, and it's just the reverse is happening. But if this light was in phase, if this was, let's say the orange light, another light, if this was in phase, that's right, and that reached point S, instead of a minimum, a maximum would be made. So it would result in a maximum if it was in phase. So the same light, which is out of phase by 180, would come over here, and the same light, even though it's out of phase, would produce a minimum, right? So we want to find out the path difference. So it should match the one for the in phase. I hope I'm making sense, right? Because this is already out of phase. So essentially we want to have, like, if we had a light which was in phase, in sync with P, or was the same light source as P from here, like from the original source, it would be in phase, and the same settings over here would produce a maximum. So that's essentially what they're asking. They've tricked us by changing the light source for Q, right? What expression could represent the path difference? So the only way the original Q, let's make it less confusing again and take Q out. The only way Q could make a minimum over here was when the original orange one would make a maximum. And how would the original one make a maximum? When it was lambda apart, when the phase difference from here was 1 lambda apart or multiples of lambda apart, right? So D and B would produce a maximum and C would produce this minimum that they're talking about, and this would just create something in between because it's not a half of a wavelength or a, you know. So the correct answer is C. Very easy question, but difficult to explain because I need more visual aid. But I hope you get it. The light source over here with is out of sync with P. It's not the same light source, and that's the gist of it.